السلام عليكم ورحمة الله وبركاته. يعطيكم العافية شباب وصبايا. Our video for today is chapter 16, which is about electricity, or in more details, the electric force, fields, and potential. At the beginning, we will talk about the electric charge, types of the electric charge, and the unit of measuring the electric charge. Therefore, the electric charge is an intrinsic property of the particles that make up the matter, where the electric charge coming in either negative charge or positive charge. Therefore, we can say the following. There is two types of electric charge, which they are positive and negative charge, commonly carried by charge carriers, protons, and electrons. Now, the unit of measuring the electric charge is in Coulomb. As an example of the types of the charge are subatomic particles, or the particles that make up the matter. For example, we know the atom, whereas the atom are composed of negatively charged particle and positively charged particles. Now, the negative charged particles, which they are electrons, and the positive charged particles, which they are the proton, where the neutron are neutral particles. As a conclusion, we can say the electric charge is the property of subatomic particles that causes it to experience a force when placed in electromagnetic field. And here I have to say that the electromagnetic field is a combination of electric and magnetic field. Second thing about the electric charge, which is the repulsion and attraction of the electric charge. And we know we have to know when we have the repulsion or attraction, or in other words, when the charge can feel the repulsion or attraction electric force. Now, if we have two likely charges, either both of them positive or both of them negative, we will have, or the charges will have, repulsion electric force, or they will repel each other. In other side, if we have opposite charges like positive and negative, then those two charges will attract each other. Now, attraction or repulsion can be described in the form of electric force, and we can use Coulomb's law as a tool to describe the electric force. As you can see here, we have two charges and the distance between them denoted by R. Now, the electric force can be given in the form of K times Q1, Q2 over R squared. Now, you need to know the following. The electric force is a vector, which means we have magnitude and direction of the electric force. This is number one. Number two, Q1 and Q2 should be in magnitude. For example, if I have Q1 like -2 microcoulomb, when I plug it in the formula, I have to substitute it as a +2 microcoulomb. K here is a constant, which is 1/4 by epsilon naught, which is equals to 9 times 10 to the power 9 Newton meter per coulomb squared. And you can use this formula or this constant to evaluate the magnitude of epsilon naught. Now, from here, epsilon naught equals to 1/4 by K, which is equals to 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. Let us go to the first example. So 2.5 kilograms spheres are placed 25 meters apart. Each sphere has a charge of 100 microcoulomb, one of them positive and the second is negative. Calculate the electric force between Q1 and Q2. We know the electric force equals to K times Q1 times Q2 over R squared. But you need to pay attention that your charge is here in unit of microcoulomb, which means I have to convert it from microcoulomb into coulomb. In other words, you need to multiply by 10 to the minus 6. Now, plug your numbers, you will get the electric force equals to 1440 newtons or 1440 newtons. The second example, as shown here, what is the electric force acting on an electron located on the line between Q1 and Q2? For this example, you need to know that you are dealing with vectors. This is note number 1. Number 2, determine in which charge you are working or your charges acting on. From this example, I have Q1 and Q2 and capital Q. And the question asking me to calculate the electric force acting on capital Q. Let me remind you with the torque. When we calculated the torque, I think from chapter 4, we said we took the our reference point, then we said the torque equal to the summation of torques coming from the whole forces acting on the lever arm. Now, let me use the same procedure. The electric force acting on this charge is coming from the electric force from Q1 plus the electric force from Q2. So let me call it F net, or F acting on this charge equals F1 plus F2. Now, F1 here, so simply F1, which is the electric force between Q1 and capital Q, and be careful, capital Q is the charge that we are calculating the electric force acting on it. Now, K, Q1 times capital Q divided by R1 squared. We have the magnitude for each term, but the direction here should be as the following. Minus or negative charge with positive charge, that means you have attraction. But we are looking to the attraction or the direction of the attraction of this charge. This charge will go all the way to the left, which means negative x-axis. Same procedure for the second force, K, Q2, capital Q divided by R squared. And the direction here, I have negative charge and positive charge. So we have attraction, but we are looking to the attraction of this charge. So it's going to be to the all the way to the right or positive x-axis. Now we have magnitude of F1 and F2 and the direction for both of them. Back to chapter 3, because we are talking here about vectors. F1 and F2, both of them on the same line, but opposite direction. So therefore, we have to subtract F1 from F2 and take the direction of the larger force. So here will be F1 minus F2, and the direction will be to the left. After I plug my numbers, I will get 0.12 nanonewton, and the direction to the negative x-axis. The second example, or actually I'm calling it the practice number 1, and I will solve this one for all of you. As shown, what is the electric or the net electric force acting on an electron located at the origin? Again, I will use the same procedure. Here, this is my capital Q, and this is Q1 and Q2. Therefore, I can say the net force acting on this charge is coming from Q1, which is F1, and from Q2, which is F2. Now, let me calculate F1. F1 equals K Q1 times capital Q divided by 1.6 nanometer squared. Now, plug the numbers, you will get 9 times 10 to the power minus 11 Newton. But the direction here, be careful. The line of the action here is along y-axis. So the direction will be either positive y-axis or negative y-axis. How to determine in which direction? It's easy. All what you have to say, okay, I have here negative and positive. That means I have attraction electric force, and the direction of the attraction of this charge, it will be all the way up to the positive y-axis. Same procedure with F2, which is K Q times Q2 divided by R squared. It will give you 9 times 10 to the power minus 11 Newton. And here I have, since I have negative and positive charge, the direction will be attraction and all the way to the positive x-axis. Now, let me draw F1 and F2. Obviously, here, F1 and F2, both of them has an angle, or the angle between them is 90 degrees. And the net force will be something like this between F1 and F2. Therefore, we cannot say, or we cannot add the magnitudes or subtract the magnitudes of F1 and F2, because each one in a different direction. One of them along x-axis and the second one along y-axis. So I can write them as a vector as this combination. Now, the magnitude of the net force for this combination will be the square root of this one squared plus this one squared. The second subject for today, which is the electric field. Now, the electric field simply is a vector, same as the electric force. And it can be defined as the electric force per unit charge at a certain point in unit of Newton per Coulomb. Let me take it as an example. What is the electric field around a positive charge, such as positive Q at point P? Okay, this is my positive charge, and this is my point P. Now, to calculate the electric field, all what you have to do is the following. Go to the point that you are looking, or that you are going to calculate the electric field around it, and assume that you have one or positive 1 Coulomb. Then do the same procedure that you have done in the electric force. Here, we do not care about the derivation. In general, electric field at certain point will be K times magnitude of the charge divided by R squared. Electric field lines. As we know, we have two types of electric charges, either positive or negative. For the negative electric charge, the electric field lines should be radially inward. But if I have a positive electric charge, therefore the electric field lines should be all the way or radially outward. Now, did we take uniform electric field and the direction of the electric field all the way to the right or to the positive x-axis, and we are going to place a positive charge or negative charge. For the positive charge, the electric force direction will be same direction to the electric field, and the negative electric charge will be opposite direction to the electric field. What about the electric field between two likely charges or two opposite charges? For the unlikely charges, we know that we have attraction. Therefore, the electric field lines should be all out from the positive charge going into the negative charge, as you can see here. And these lines is the electric field, are the electric field lines. Same procedure with the likely charges. we know the electric charges will give us, or will feel, actually they will feel repulsion, and the electric field lines should be something like this. First example about the electric field, as shown here. What is the net electric field at point P? Okay, I will use the same procedure that I used in the electric force with a small difference. At the beginning, we are calculating the electric field at point P. Where is my point P? It's right here. Now, you have to assume that there is a test charge, positive test charge of 1 Coulomb, or positive 1 Coulomb, and do the same as you did in the electric force. Now, the electric field here equals to, I mean the electric field at point P is coming from Q1, which is E1, plus the electric field coming from Q2, which is E2. Let me calculate E1. E1 is K Q1 divided by R1 squared. Do your calculation, you will end up with 18 times 10 to the power 2 Newton per Coulomb. But the direction here, we know this negative charge, and we assumed a positive charge at the point P. Therefore, we have attraction, and the attraction of this test charge, the direction of the attraction of this test charge will be all the way to the negative x-axis. The same procedure for E2, you will get 4 times 10 to the power 2 Newton per Coulomb, but the direction here, you have positive and positive, so it will be repulsion, and the repulsion of this test charge will be all the way to the negative x-axis. So from here, E1 and E2 have the same direction. Therefore, we can say the net electric force, the net electric field equals to E1 plus E2 and the direction to the negative x-axis. This practice, what is the net electric field at point located at the origin? I will leave this for all of you as practice, same as what we did in the electric force. The third subject, which is the electric potential at any point in the space. Now, let we assume we have Q, and we are looking to calculate the electric potential at point P, a part or a distance between capital Q and point P denoted by R. Now, the electric potential at this point is produced by the capital, or by this charge, is given by V equals to K times Q divided by R. And be careful, the electric potential here is a scalar quantity. It's not vector. Therefore, we are taking here the charge either positive or negative. We are not taking the magnitude of the electric charge. Number 2, the unit of the electric potential is in volts. Number 3, when we are talking about electric potential, in other words, we are talking about characteristic of the electric influence from this charge all the way into this point in the space. What is the electric potential at point P? Guys, here we are talking about electric potential, not electric force or electric field. Okay, I will use the same procedure, but you need to pay attention that the electric potential is not a vector, it's a scalar. So we do not care about attraction or repulsion. We are going to add or subtract the potentials. As you can see here, the electric potential at point P is coming from Q1 plus the electric potential coming from Q2. And we know the electric potential is given by K, Q1 over R1 plus K, Q2 over R2. Be careful, Q1 here, when you plug it, you have to plug it minus 6 times 10 to the power 9, minus 9 Coulomb, because it's nano and negative. Keep it. It will give you 15 volts.